All right, let's dive right into this explainer and uncover the core technology that literally sparked the modern AI boom. If you've been following the rapid, honestly mind-blowing advancements in artificial intelligence lately, you've definitely seen incredible feats of text generation, image creation, and complex problem solving. But behind almost all of these seemingly magical leaps is a very specific structural foundation. So today we're going to completely demystify the transformer architecture. We'll break down exactly what it is, how it processes information, and why it absolutely reshaped the entire landscape of deep learning. To understand why modern AI works so incredibly well, we first have to answer a super basic question. What does the T in ChatGPT actually mean? I mean, we hear the term everywhere, but that T is the key to the whole shebang. It stands for transformer, specifically a generative pre-trained transformer. Now, the transformer isn't just a single piece of software. It's actually an entire family of artificial neural network architectures. It's a completely new way of building neural networks that has essentially become the gold standard for deep learning today.
Let's rewind a bit to the AI training bottleneck, looking at the landscape right before this massive breakthrough.
You see, before 2017, training an AI to understand sequences, like a simple sentence of text, was a massive, incredibly time-consuming headache. Previously, the dominant architectures were recurrent neural networks, or RNNs, and specifically a type called long short-term memory networks. These older architectures relied heavily on recurrent units. Basically, that meant they had to process data sequentially, word by word, step by step. You literally couldn't process the end of a sentence until you had processed the beginning. Transformers completely changed the game because they have the distinct advantage of having absolutely zero recurrent units. By totally stripping those out, transformers can process data in parallel, fundamentally slashing the training time required and allowing developers to train massive models so much faster.
Which brings us to a major paradigm shift. Attention is all you need.
Back in 2017, researchers at Google published a paper with that exact title, Attention is All You Need. Now, they were originally just trying to improve machine translation software, but their core solution proved revolutionary. They introduced the multi-head attention mechanism. This is the very heart of the transformer. Instead of looking at a sentence word by word, a parallel multi-head attention mechanism looks at all pieces of data at once and contextualizes them within a massive context window. It evaluates how every single piece of data relates to every other piece simultaneously. By doing this, the architecture can amplify the signal for the key, most important information, while effortlessly tuning out the less important background noise.
So, let's look under the hood at how transformers actually process data, the core mechanics. Let's break down exactly how this multi-head attention turns raw, messy data into intelligent output. It's an elegant, multi-step process, kind of like a giant puzzle that allows the network to handle incredibly complex inputs. In step 1, the architecture takes in the input data. And hey, this doesn't just have to be text, it can be images or audio too. In step 2, that raw data is chopped up and converted into a sequence of numerical representations called tokens. Then, in step 3, every single token is converted into a vector by looking it up in an embedding table. Finally, in step 4, at each layer of the network, every token is contextualized with all the others via that parallel multi-head attention mechanism we just talked about.
But analyzing everything all at once presents a unique challenge, right? Because the self-attention mechanism processes everything simultaneously, researchers call it permutation invariant. That's really just a fancy way of saying the mechanism on its own doesn't actually know what order the words or data came in. It just sees a big pile of vectors. So to solve this, transformers do something really clever. They inject positional information directly into the data. By using learned positional embeddings, the network retains the structural order. This ensures that the sequence of a sentence still critically affects the final output, even though it's all being processed in parallel. Moving on to the architecture variants and how researchers are tailoring the tech. As this technology matured, the foundational architecture from 2017 branched out. Researchers began customizing it for very specific AI tasks. Today, modern transformer designs are usually grouped into 3 distinct variants. First up, we have encoder-only variants. These are highly optimized for representation learning, basically grasping deep context within a dataset. Then we have decoder-only variants. These are built for autoregressive generation, meaning they excel at predicting the next word in a sequence to generate long-form text. Finally, we have the encoder-decoder variants, which combine both to handle conditional sequence-to-sequence tasks, like taking a whole sequence of English text and outputting a sequence of French text.
Okay,
Let's look at the real-world AI impact, which stretches way beyond just language.
It is wild to see the explosive real-world results of adopting these variations to train massive datasets. The impact has gone so far beyond the initial goal of just machine translation. Just looking at the timeline highlights how rapidly this architecture completely took over the field. Following that 2017 paper, the tech was quickly adopted to train large language models, leading directly to systems like BERT, which stands for Bidirectional Encoder Representations from Transformers, and of course, the Generative Pre-trained Transformers, or GPTs, that are dominating headlines today. But it didn't stop there. The same architecture has found incredible success in reinforcement learning, processing audio, playing complex games like chess, and multimodal learning. It's even being used in computer vision through vision transformers and is actively shaping the future of robotics right now.
So I want to leave you with this final thought. Think about a technology that was designed just a few years ago to fix a speed bump in machine translation. It has systematically revolutionized how machines process text, sight, and sound. It really forces us to ask, as developers continue scaling these models and feeding them even more massive datasets, what complex human tasks will the transformer architecture conquer next? It's a fascinating space to watch. Thanks for joining me for this explainer, and I hope you now have a much clearer picture of the mechanics driving our modern AI revolution.